Adrian says that the closed loop system is stable if and only if the Nyquist plot does not accept -1. Under which condition does it apply? You only apply if L naught is open loop stable. Okay? So this is the assumption before Nyquist stability criteria can work. Alright? So if you just tell me that the closed loop system is stable if and only if Nyquist plot L naught does not accept -1, it's only half the answer. The other half of the answer is that L naught must be open loop stable. Okay? Question 7, tested last year. Draw a Nyquist plot of stable closed loop system and for an unstable system. You can draw me a stable closed loop system very easily with your eyes closed, I think. Right? Just draw me something like this. Okay? And the Holy Bible, we have seen this multiple times, and I believe you can draw it in order too. So it's a simple second order L naught. Alright? And you can easily label what is A margin, what is vector margin, what is phase margin. Yes? That's not difficult. Explain the meaning of A margin, phase margin, and vector margin, then there's a problem. Okay, so you're supposed to tell me in words. Alright? In words. That A margin, Km, is the additional gain by which L naught may be multiplied so that it reaches -1. Okay, how much additional gain before the system becomes unstable? It's also fine. Phase margin is the additional phase delay which can be added to L naught to reach the critical condition. Okay, if instead of saying to reach the critical condition, you must tell me that before the system becomes unstable. That's also fine. Vector margin. Okay, you can tell me that gain, phase margin are traditional indicators of relative stability. More informative measure is the vector margin, which is Sm. That is the distance from -1 to the closest point of L naught. Okay, but if you tell me that vector margin is the distance from -1 to the closest point of L naught, that's also fine. Okay, but if you can't tell me everything, of course you have to ask. But this is only half the answer. The other half of the answer is you have to draw a Nyquist plot for an unstable system. And similarly, we haven't really covered this, but in the lecture slides, you will notice that we have an example of an unstable system which looks like fish. Okay? And that's the answer that you'll be drawing. So you should give me another plot. Unstable closed loop system, and you draw me a fish in the slides. Alright? Okay? Question 8. This is also tested before. On Nyquist plot for closed loop system, a phase margin of 150 degrees and a frequency of 3 Hz. And a gain margin of 11.6 dB will be right. So if you are given 120 degrees at a frequency of 3 Hz, okay, and you are given a gain margin 11.6 dB. Okay, can you tell me how much can the plant gain increase before the closed loop system becomes unstable? And what additional delay can be added before stability starts? Okay? So what does 1.6 dB mean? You have to convert this to raw number. You see your calculator. dB is 20 log base 10 of x. Okay, so 20 log base 10 of x is 11.6. That's x. X is 3.8. So we will calculate now, you can try. Okay, 20 log base 10 of x is 11.6. Okay, see for yourself that x is 3.8. Okay, and with this, we know that gain can increase by 3.8. You understand? Okay, so every single one of you whoever has a calculator, please make sure that you take it. Okay? Next. For phase margin, we tell you that it's 120 degrees at 3 Hz. So what does that mean? Degrees is degrees. Alright? Hertz is frequency. Alright? We asked about the plant delay. Plant delay is in seconds. So it's supposed to give me an answer in seconds. Alright? Frequency is Hertz. Okay? It's also 2 pi. You can convert Hertz to 2 pi easily. Okay? 2 pi is 1 revolution. Okay? So 1 revolution in degrees is 360. Okay? So 120 over 360, which tells you the number of revolutions. Alright? Times 1 over 3 Hz in terms of height, radians. So 1 hertz will give you radians, yeah? So 1/3 of 1 revolution is 0.11 seconds. Alright, so the maximum delay you can add to the closed system before it becomes unstable is 0.11 seconds. Okay, of course, if this is going to come as an exam, the numbers will be exactly the same. Alright, but the method is this. Okay, so let's start with the log. Okay, next question 9. Show the overload structure. Ideal compensator should cancel the plant dynamics and state the drawbacks of the approach. Describe a feedback system that can provide approximate plant inversion. So these are all very aliens, but I tell you that these are all in the lecture notes. They are supposed to read. Okay? So, this is all from the lecture notes. Alright? It's easy to understand this. Because if you look at this, it's telling you that this is open loop control via implicit plant conversion. Just understand now, okay? Just understand now. If you want your output Y to follow your reference R, what do you want in between? You have plant P, right? So it will be good if your controller C, okay, has a feedback here which is PS. Why? Because what it means is that you effectively will have something like this. So you have C equals to P inverse. So if P inverse times P is equal to 1. Okay, if that's the case, Y is wrong. Alright, but this is explicit plant inversion, but you can't really do this because you don't know what is P in most instances. Alright, what you can do is you can also try this, which is implicit plant inversion. Okay, so the idea of plant inversion is if you know the effect of the input and the output, you have accurate model of the plant, you can invert the relationship, okay, such that you have a controller which is P inverse, P inverse times P is equal to 1, and then Y is equal to 1. Okay, so the idea is if the controller C is P inverse, CP is P inverse times P, that is equal to 1, and Y is exactly equal to 1. Alright, but there are limitations, which means that you must know P exactly before you can set that C is P inverse. Okay, P must be stable, and if you have disturbance, it must be measurable. So all these are serious limitations because when you control a plant, you do not know what the plant is exactly. Alright, so can you actually use this in real life? Okay, but it's good to know. Alright, okay? And if this is tested, you also have to continue to do this. Okay, but of course you're not expected to give me a exactly answer. Just tell me something roughly like, draw me the plot diagram, and tell me that C is P inverse. Okay? When you C is P inverse, what is R? That's all. Okay? And the limitations are that you must know what is P must be stable. Okay, your disturbance if present must be exactly measurable. Okay, and P inverse must be stable and realizable. Okay? Question 10, important, but I'm not going to go through this again because we have gone through this multiple times. You should know the answer. And all in all, I will be uploading this set of solution. So practice question on Moodle. And actually practice some of you may have this because this is not different from okay? This is something that I taught myself. So those of us who already have this. Please, the reason why I perform this is because all this question will came out multiple times in the exam. I'm not sure if it's going to come out exactly wrong. Please don't quote me for this. But since it has came out before, it tells you that it's in the scope of this lecture. You understand? Okay? Any questions? No? Alright. So if there are no further questions, let's move on to the next part of the lecture. The last part of this lecture on state space. Okay, so all in all, important areas. Okay? Distinctly three important areas. The first area is on stability, margins, and sensitivity functions. Okay? Is that clear? Stability, margins, and sensitivity functions. That's the first area. Alright? But of course, before you can ever go into that, you have to tell me what is called why in relation to the reference, the disturbance, and the measurement nodes. Okay? So that's the first area. Second area. Okay, the second area is on PID controller and home placement. Okay, with the diagonal equation. Alright, that is where you look at PID controllers as a polynomial transfer function. Okay, and you do home placement for CS, which is GS over HS, so everything is polynomial. Okay, the very last part of the lecture is on state space. Okay, so in state space, what we're going to learn is how do you represent the system in state space? How is it related to transfer functions? How do you actually control a system in state space? And how do you observe the system in state space? Okay, so this is what we're going to learn from state space. Alright, this is week 5. Okay, week 5, 6, 7, 8, 9, 10, 11, 7 more weeks. Alright, so we are going to leave maybe at least one revision lecture, 2. This means that we need to complete this entire part of the lecture in maybe another 5 weeks. Okay? Alright, I can understand that you guys are a bit tired after that, about 1 hour of revision or so, but please, for now, because this is such an important chapter, I think you guys will want about how to focus on revision lecture. Yes? Okay? So let us just continue for another 45 minutes. Basically, an introduction to this. Alright, it will be easy. It's not so taxing. But the main thing is you have to focus. Because if you're not focusing, there's no point in us going through this. Okay? Alright? Any objections? No? Okay, so then I expect focus. Alright, so what's the state space model? There are actually many alternative model formats, as we say, for linear dynamic system form that is function. Okay? So if you have a single input, single output, single input means that there's one U, one R, one reference. Okay? Single output means there's only one Y, which is what we call in short, single input, single output, etc. So the representation is as good as any other. You can write it in transfer function. Okay, you can write GS is Y over R. You can write it in state space, never mind, because it's significant. Okay? But when you move to more complex problems, that's when I tell you that, hey, I want to measure the angle of rotation of the robot arm. I also want the speed, I also want the acceleration. So it's like what I want. And I want to control both the angle and the speed. I want to control these. So I put inputs and 3 outputs. Okay? So this is multi-variable problem. Multiple variables. Okay, so multi-variable. It's designed to use some special model formats, and one of the most flexible format you can use is the state space model. Okay? So we will examine the linear state space model in a little more detail for single input, single output case. And some of these ideas we can carry over to the multiple input, multiple output, which is MIMO case that we will study later. So in particular, we will study this thing called similarity transformation, okay, which I'll tell you in further detail, and equivalent state representations for both a controllable system and a observable system. What are the state space model properties such as controllability, can you control the system, reachability, can you reach the final solution, can you stabilize the system, can you observe the system, if you can't measure it, so can you observe it, can you reconstruct based on this thing that you're observing, you can actually detect the solution. Okay, and some of the special canonical model formats of this case. Okay, just revision. Remember a pendular system? It's just a revision, copy it as everything. Okay? So if you have a differential equation for a pendular system, alright, what you can do is you can, because it's a non-linear system, sine theta. So this side assume theta is small, sine theta is just theta. You form a differential equation, second order. Okay? And this, my Laplace transform is this. But it's not required, you don't write state space. model. Alright, you want to do the Laplace transform. All you need to do is define your states, x. So if you define your states x, because it's second order, so logically we have theta dot over theta. Divided from it. Alright? So next you need to actually form your state space model, which is x dot is ax plus bu. Okay? So x dot, x is theta dot over theta, so x dot will be theta double dot over theta dot. Okay? Equals to ax, x is theta dot over theta, plus bu, u is your tau. Okay? All you need to do is just find out what is theta double dot. Theta double dot is minus c over I plus theta dot, minus mgl over 2I plus theta, plus 1 over inertial I times tau. Okay? What is theta dot? Theta dot is just theta dot. 1 times theta dot plus 0 plus 0. Okay? So once you have this, the other part of the space model other than x dot is ax plus bu is y equals to cf plus du. Okay, so y, if your y is your angle, you are looking for only one output. Y is angle theta. Theta is c, x is theta dot over theta plus bu. Because this is just theta t, the left hand side. So on the right hand side, only one theta t. Okay, so 0 times theta dot plus 1 times theta t plus 0 is theta t. Okay, so your c is 0, 1, and d is 0, 0. Okay, so this is just a revision, which is in the notes, something like this. So that eventually A is this, B is this, C is this, and D. Alright? Is this online? I think so. Okay, if you don't find this, you let me know. You have copied this already, the last time. Okay, so you can also look at the transfer function. Okay, and instead of having minus c over I and minus ml over 2I, you can just write it as 2 zeta omega and minus zeta omega squared. Okay? And if you have this, from here to here, you actually derive. You know how to derive? You know how to derive if I put a transfer function in this space model? No, very good. If you don't know, tell me, right? Okay, so this is what you do. If you have a transfer function like this, okay, PS, which is theta over T, T is top. I used to swing the rubber arm. It's 1 over inertial I over S squared plus 2 zeta omega S plus omega squared. Next, what do? Just multiply. Okay? Theta S times S squared plus 2 zeta omega S plus omega squared equals to 1 over inertial and dt. Okay, expand. Okay, and do the inverse of the first transform. So you form your differential equation. Before you can write a state space model, you only need one thing. You need your differential equation. Okay? So you must get your differential equation like this. After you get your differential equation, you define your states. Okay? So you can define xt, which is a state, theta dot over theta. Okay, next, you know that state space model is x dot equals to ax plus bu, and y equals to cx plus bu. Okay, where the inertial condition is just x naught. Okay? Once you get this, you need to write down what is x dot equals to ax plus bu and what is y equals to cx plus bu. Basically, you can identify what is a, b, c, and d. Alright? We already defined that x is theta dot over theta. So x dot is theta double dot over theta dot. Okay? So this x dot equals to a x, which is theta dot over theta, plus c u. U is just t. How? Okay? Next, what is theta dot? What is theta double dot? You can get from this equation. So theta double dot is minus 2 zeta omega n theta dot minus omega n squared theta plus 1 over I times tau from here. Okay? Now what is theta dot? Theta dot is just 1 times theta dot plus 0 times theta plus 0 times. Okay? So this is half the answer. The other half the answer is y equals to cx plus du. So y, if you have output y, which is your angle, theta, theta equals to c, x is theta dot theta, plus du, u is tau, t. So C is 0 times theta dot plus 1 times theta plus 0 times this. Okay? So this is how you go from here to here. Alright? Okay? So you see that you can go either from a differential equation to a state space model, or you can go from a transfer function to a differential equation to a state space model. Okay? Alright. So let's go to a formal definition of what's a linear continuous time state space model. So a continuous time linear time invariant state space model take this form. X dot is ax plus bu and y equals to cx plus bu. And all these are in terms of time t. Okay? And the initial condition x0 is x0. Where x is the state vector, u is the control signal, y is the output, x0 is the state vector at time equals to 0. And ABCDs are matrices of appropriate dimension. Okay, so if this is a second order, A is 2 by 2. B is a vector. Okay, 2 row and 1 column. C is also a vector, or is 1 row and 2 columns. D is a vector, 2 row and 1 column. Alright? Okay, so next, if you have a state space model, x dot equals this, and y equals this. Alright, you can take the Laplace transform of the state space model. Okay, so if you have the Laplace transform b over dx over dt, you get s xs minus x0. Alright, and everything else is the same, just as in previous situation. Alright, and next, if you can do this, you can collect xs on one side and shift this to the right hand side. And this. Okay, so if you collect xs on one side, you have sxs minus axs, so it's si. Because now you are dealing with matrices. You can't just write s minus k. Okay, because s is just frequency. It's just j omega. Alright, so you must have identity matrix I, which is on the same order as A. Okay, so si minus A, bracket xs equals to 1 by 1 on the right hand side. So xs will be, we move this to the right hand side, which is si minus A bracket inverse x0 plus si minus A bracket inverse B inverse. Okay? So if you can collect this, alright, remember that ys is cx plus bu. Okay, so substitute x inside. So ys is c times x, so c times x. So c bracket si minus A inverse times b from here. Okay, with the d by us function plus your du plus c times si minus A inverse. Okay? And because you know that gs is a system transfer function, okay, so gs is ys over us. Basically gs, alright, ys divided by us, which is this part. C bracket si minus A inverse b plus b. Okay? I hope you can follow this. If not, I will repeat this again. But just understand that in summary, transfer function describe the equal properties of linear systems in algebraic form. Okay? So let me just recap on what I just said in a lot more detail. Okay, if you have a differential equation, x dot mdx plus bu plus cx plus b, you can take the Laplace transform. The left hand side, right hand side. That's what I get. Okay, collect the terms of xs on the left hand side, and have si minus A xs. K equals to y on the right hand side. Okay? And you want just xs on the left hand side. So what do? You have si minus A, right? You need to multiply this by si minus A inverse. Because the inverse times the matrix will give you I, which is the identity matrix. The identity matrix times the s xs will give you xs. Do you understand this? Yes? So if you multiply by the inverse on the left hand side, you multiply by the inverse on the right hand side. So they are equal. What is I? There are many values of I. I can be scalar. So I can be 1. I I can be 2 by 2. Okay? And identity matrix, if it's 2 by 2, it's just 1, 0, 0, 1. If it's 3 by 3, we have a third order system. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. You know this, right? Okay? Alright, next is if your x, your state vector, is defined as theta dot beta. Okay, the identity matrix 1, 0, 0, 1 plus theta dot beta will give you just theta dot beta. You understand this? Yes? Okay? Next, after you have multiplied by the inverse on the left hand side, you have this xs is si minus a bracket inverse x naught plus si minus a bracket inverse b s. Substitute this into your y equation. So you have your c on all the terms, and then du, which you carry over. You collect the US terms, and you leave with the inertial condition over here. Transfer function gs is u y over us, so you can see where it's going. Okay, c times si minus a inverse b for p. What does this mean? If I give you c, I tell you c is 0, 1. Okay? It's a second order system, so I is 1, 0, 0, 1. A, if you know A, minus 2, minus 3, 0, 1. If you know B, 1, 0. You know D, 0, 0. Plug the vectors inside. And you can form your transfer function in frequency domain. Okay, it's as powerful as this. If you have a state space model, immediately understand that for state space model, the transfer function is this. You can ask the exam question. What is GS? GS is C bracket si minus A inverse B. Okay? If you are asked to derive GS, you derive this thing. Okay? Alright? If you ask to write down what's the transfer function for the state space model, and they give you A, B, C, D, they might ask you to write down what's GS in polynomial. Alright? Do you understand this? Yes? Okay? Any questions? I think this is all. Alright, so that's very standard revision thing. Okay? We have covered this in the revision for the first part as well. I'm going to do such thing. Alright, next what we want to do is if you have a state space model, okay, how do you do feedback control? Because this is a control module, right? We don't just talk about mathematical representations. We want to control this. Okay? So, for state feedback control, by the name itself suggests that we are going to feedback the states. Okay? So for state feedback control, we're going to feedback the states. We're not feeding back the output, we're feeding back the states. Consider a standard state space system, this. And if the system has certain properties, what we want to do is we want to move the eigenvalue, which is equivalent to the poles of the system, any arbitrary location, using a simple proportional feedback of the full state, u equals to minus k. Okay? Alright, so in state space controller design, we say that the concept of state feedback control, which means feeding back the states, they will require the knowledge of x. Alright, because we're going to feed back as input u is minus k proportional gain times x. But now because x can be 2 by 1, okay, x can be 2 by 1, vector 2 by 1. Your gain is not a pure gain. K is also a vector. Okay, so that this times this will give the scalar u. Alright, so this feedback control, state feedback control. Okay, and state estimation, whereby you don't know what exactly is the state, but you can measure. Okay, so you can do some estimation of states. And these two will require some further analysis of the properties of the state model. What you can do is you can use similarity transformation to understand some concepts of how controllable the system is or how observable the system is. far? How good are you with eigenvalues? Never mind, it's okay. It's okay if you don't know at this point that you don't know what is Z, right? So it's better to say you don't know at this point. Okay, so let's go through some basic mathematics. You know NTU, today NTU was in the news. They converted their classrooms to flipped classrooms. Flipped. Meaning instead of the lecturer just telling you what to do, they do a learner-centered approach. And by learner-centered approach, it's something similar to what we're doing now. We give the materials to you before you. We ask you to do a quiz when you come into the classroom. So you do a quiz. Provided you have already learned the materials, right? By yourself. So you do a quiz, then we know that, oh, there's something. So you learn that you understand. Okay? Then we will gather you into small groups to do group discussion. Okay, then maybe you can come and present some answers to what they are doing. Flip learning. Hoping that you guys will learn more from what you can discover through Google, through Wikipedia, through whatever online resources and notes. And then you come to the lecture or the tutorial, just figure out what else is it that you do not know. Maybe you can do that. Okay. I'm sharing this on the news that I read today. Okay, so this is more still on a teacher-centered approach, okay, and learner-centered approach. As long as you learn the materials, it doesn't matter which approach. Okay? Alright, so that's the basic mathematics. Okay, basic mathematics, without. Are you ready for this? I think this is online. I have a copy. Just understand. I have a copy for you. So basic mathematics, without stepping back control. So there's no feedback.
Your cancer.
No feedback. Okay?
Senior training.
This is your system. So now onwards, you're going to write a system like this. Okay, instead of P, you write down x dot equals to ax plus bu. This is your system. What does it take in as input? It takes in u. What does it provide as output? It provides x instead. Okay? And x times c will give you y. Okay, but y was supposed to be cx plus du, right? Yes? So now there's no u at the time being. We tell you that e is 0. Okay, without any state feedback control. Alright, so this is how you should draw this. Next, if I give you an example of what is ABCD, so if this is a second order system, A can be minus 1, minus 2, 0, 1. B can be 0, 1, C can be 0, 1, 0. You know that your transfer function, which we have derived just now, GS, is C times Si minus A inverse B plus D. Okay? Next, we can plug in what is ABCD in this. So if you plug in what is ABCD, basically C is 0, 1. So bracket is 0, 1. Okay, in big brackets, Si, which is S times 1, 0, 0, 1, will be S 0, 0, S. S is scalar. Okay? At any point in time, you don't understand, just raise up your hand. Minus A, minus 1, minus 2, 0, 1. The whole thing bracket inverse. So if you do not know how to compute inverse matrix, please go back and learn. Alright? B, 0, 1. B, 0, 1. Of course, I will teach you a little bit about it. You see this? You combine these two. S minus minus 1 is S plus 1. 0 minus minus 2 is 2. 0 minus 0 is 0. S minus 1 is S plus 1. Okay, inverse like this. Okay, so how do you compute the inverse? Okay, you swap the diagonal terms. So you shift S minus 1 up and S plus 1 down. Okay, and you multiply the negative to the other diagonal. So 0 plus minus 0 is 0. 2 becomes minus 2. Okay, divided by the determinant. So what's the determinant? The determinant is S minus 1 minus S plus 1 minus 0 plus minus 2.
Ada wire.
Okay? So to do the inverse of the matrix, you come up with the joint over there. Determinant. You learned this before? Yes. I say yes. I didn't know yes. Okay? Alright? Next. Okay? S plus 1 plus S minus 1 is just S squared minus 1. Okay? Then 0 times S minus 1 is 0. 1 times 0 is 0. So we still have together is 0. 0 times minus 2 is 0. Plus 1 times S plus 1 is S plus 1. 0, 1. Okay? Next, 0 times 0 is 0. S plus 1 times 1 is 1. So 0 plus S plus 1 is S plus 1 over S squared minus 1. So this is a transfer function for GS. Okay? So can you see that if you have vectors and matrices for A, B, C, D, you can find out what is GS from the state space model. Next, how is it related to what I was going to tell you? So I ask you, you don't understand what's eigenvalue of poles, right? Because you said no. So if you look from here, what's the pole of the system? The pole of the system is the solution of the denominator. Okay? And the denominator is S squared minus 1, equal to 0. So what's S plus minus 1? What is eigenvalue? Eigenvalue you can get it from A. Okay? So eigenvalue of A, which was minus 1 minus 2, 0, 1. What you do is you find the determinant Si minus A. You put that 0. But you already know the determinant because the determinant is here. S squared minus 1. Yes? Okay, when you computed this, you already know the determinant. Si minus A. That's S squared minus 1. Okay, so if we put S squared minus 1 to 0, we have S plus minus 1. So we tell you that the poles of GS is the same as the eigenvalues of A. You get that? Yes? Okay. Any questions? Okay, if there are no further questions, let's move on. The next slide is, I don't think I understand anything from here. Okay, so what we're going to do, we're going to do this. This is on board, so that's not important, right? If you want to, wait, what's the excitement about? You still need this? Was anyone copy? No, right? Is anyone copy? No. Okay. So it's okay, we move on, right? Yes? Okay. So that one was without state feedback control. Now we want to look at state feedback control. Okay? So what is state feedback control? State feedback control is the concept of feeding back the states. Okay, so in block diagram format, tell you that this is x dot equals to x plus bu. Input is u, output is x times c is y. Okay, because y is x plus du and b is same as u plus c. Okay, so with state feedback control, what I want to do, we want u to be minus ax. So basically, you take the states out, you'll notice that it's a double arrow. It's not a scalar, it's a vector. Okay? This is the star. Because in the exam, you will be asked to draw the block diagram illustrating state feedback control. So if you're asked to draw a block diagram illustrating state feedback control, you draw this. Okay, and tell me that u is minus ax. If I don't see the double line here for x, I'm going to deduct marks. Let's see where that. Okay? Because this is not scalar, it's a vector. Any questions? Okay? Let's move on. So what does that mean for a space closed loop system? I call this closed loop because there's now feedback. Okay? I think if we have finished, this page, we'll just end it. Because I can see that you guys are already drifting away. And I don't like to keep talking when you guys are not listening. So there's no point. Okay? So if you want to stay focused for another 5 to 10 minutes. Then you can do that, right? Yes. So we want to look at closed loop system. So originally open loop system was x plus ax plus b u. Now u is minus ax. Okay? X here. Group the x together. So you have a minus bk x. Okay? And I tell you that a minus bk is ACL. Alright? And y is ACL for the equation. So in closed loop system, okay, your a is now a minus bk. If you do a Laplace transform of equation 1, you end up with s xs minus the initial condition plus ACL xs. You group the xs together, you end up with si minus ACL s plus x0. You just shift this to the left hand side, shift this to the right. Okay? And you shift this over the other side because you want s. So you have si minus ACL and x inverse is not. You substitute this back into equation 2 for output. So output is ys equals to c x plus du. C x plus du. Okay? U is now minus kx. So minus bkx. Okay? If d is 0, it is 1. If d is 0, and we end up with this. Y is c bracket si minus ACL bracket inverse. I wrote this as a minus bk purposely. Now we have ACL as a minus bk. Okay, and what does this tell you? End of the day, that if you are looking for closed loop poles, you are now looking for the eigenvalues of a minus bk. When you were looking at the open loop control without feedback, the poles of the system are the eigenvalues of A. Now with feedback, the closed loop poles are the eigenvalues of A minus B. Okay? And the closed loop polynomial, if you're asked to find out what is the characteristic of polynomial, so-called closed loop polynomial, all you do is to solve for the determinant as I minus A minus B. Okay, so basically you solve determinant as I minus A minus B equals to 0. If you can solve this, you get closed loop poles. Okay? Alright? Do you understand this? Which relates to your open loop case. Okay, so if you understand this, I said this is the last page. Let me just show you what's inside. Very quickly. Closed loop system, ACL x. ACL is